In this lesson, we're going to see how changing the frequency of the oscillator will affect the waveform. Let's take a look at the next section of code in the basic saw function. That would be phase equals phase plus 2 pi times TS times frequency. This is our phase incrementer. Notice we have TS inside of here. In order to see the value of TS, we need to go to the constants.h file, and here it is. TS is 1.f divided by sample rate. And of course we know sample rate is 32,000. So TS equals 1 divided by 32,000. And when we divide 1 by 32,000, we come up with 0.00003125. TS is a fraction of 1 second. If we chopped up 1 second of time 32,000 times, we'd end up with 32,000 values of 0.00003125 seconds each. If we multiply 32,000 times 0.00003125 seconds, it will equal 1 second. Now keep in mind our range of phase is 0 through 2 pi. But the faster our oscillator frequency is, the faster we travel through this range. Let's run an example. If Hertz equals 1, and the phase equals 0 because we're starting at the beginning, then we change phase equals phase plus 2 pi times TS times op frequency into phase equals 0 plus 6.28 times 0.00003125 times 1 Hertz. And that will equal 0.00019625. This result is the value of our incrementer at 1 Hertz. So at 1 Hertz, the incrementer will add 0.00019625 to phase after each sample rendered. So what value would we see at the 32,000th sample? 32,000 times 0.00019625 equals 6.28. This is 2 pi, and this would be the end of our waveform cycle. And for reference, let's divide 6.28 by 0.00019625, and our result will equal 32,000. We will do these simple mathematical equations again in the next examples to see how many samples it takes to fulfill the range of 0 to 2 pi. Now let's do a couple more examples. If we made Hertz equal 2, then the incrementer formula would be phase equals 0 plus 6.28 times 0.00003125 times 2, which would result in 0.00003925. So this is our new incrementer at 2 Hertz. And like we did before, let's multiply 32,000 by the 2 Hertz incrementer value of 0.00003925. And the result is 12.56. Now we see we have been through 2 complete phase ranges because 6.28 times 2 also equals 12.56. And if we divide 6.28, which is just 1 full phase range, by 0.00003925, the result will be 16,000. This is half the amount of samples in 1 full phase range, so we now have 2 full cycles using the same 32,000 samples per second. Let's try one more at 4 Hertz. Phase equals 0 plus 6.28 times 0.00003125 times 4 equals 0.000785. So this is our new incrementer. And if we take 32,000 times 0.000785, it will equal 25.12. Now we have 4 complete phase ranges because 4 times 6.28 equals 25.12. And if we take 6.28 and divide it by 0.000785, it will equal 8,000. And this is 1/4 of 32,000 samples. Some of the key elements that we're discovering here is the oscillator will always generate 32,000 samples per second. The amount of samples used to create one full wave cycle depends on the oscillator's frequency. And the higher the frequency, the less amount of samples we use for each wave cycle. Now let's run through a sequence of examples using the entire basic saw function. We are going to start the phase at 0, and our frequency is going to be 5,000 Hertz, and amp will be 1. Now remember, we are working with our final value to be a maximum low of -1 and a maximum high of +1 with 0 in the middle. The first calculation used in our basic saw oscillator will be out equals 0.5 F times amp times phase divided by pi. The reason we're using this is because phase is currently 0 and it's less than pi. So we plug in our values. Out equals 0.5 times 1 times 0 divided by pi. We can quickly see that this will give us a 0. 0.5 times 1 times 0 is going to be 0. So we move to the next operation, the incrementer, which is phase equals phase plus 2 pi times Ts times frequency. When we plug in the values, what we end up with is phase equals phase plus 6.28 times 0.00003125 times 5,000. Our result is we get phase equals 0.98125. When we calculate the next sample, we will use this 0.98125 phase value. The last operation in the basic saw function is return out, which will return a sample value to the wave compute function, which in turn passes the sample value to the make sound function, where we have y equals wave compute f0. Eventually, the sample will be converted to a 16-bit value, which will be stored in the audio buffer. This process happens between every sample we render. If we are still inside make sound's for loop, we'd run basic saw again. When we return to basic saw, phase is still 0.98125, which is less than pi. So we're going to use this formula again. So we plug in the values again and end up with out equals 0.5 F times 1 times 0.98125 divided by 3.14, which evaluates out to out equals 0.5 F times 1 times 0.3125, with a final result of out equals 0.15625. Before we return our out value of 0.15625, we are going to run our phase incrementer again. But this time it will be phase equals 0.98125 plus 6.28 times 0.0003125 times 5,000. 0.98125 is our previously calculated phase value. And as long as we don't change the frequency value, we can continue to use 0.98125 as our incrementer each time we update the phase. Let's calculate it now. Phase equals 0.98125 plus 0.98125. So now phase equals 1.9625. We return the sample value of 0.15625, and when we return for a new sample, we find we are still between 0 and 6.28. We are also still less than pi, so we will still use the if operation. And our new numbers will be out equals 0.5f times 1 times our phase value of 1.9625 divided by pi, which is 3.14. That comes out to be out equals 0.5 times 1 times 0.625, which equals 0.3125. Next, we increment our phase again. Phase equals 1.9625 plus our incrementer of 0.98125. Now phase equals 2.94375. We've returned the sample value of 0.3125 and head back to get another sample. Again, phase is still less than pi. So now out equals 0.5 times 1 times 2.94375 divided by 3.14, which will become 0.5 times 1 times 0.9375, which equals 0.46875. We increment again and come up with phase equals 2.94375 plus our incrementer 0.98125 equals 3.925. Again, we return the sample value of 0.46875 and head back to get another sample. But now phase is greater than pi, but it's still between 0 and 6.28. So we must use the else method, which is 0.5 times amp times phase divided by pi minus 2. So we plug in our values and we get out equals 0.5 times 1 times 3.925 divided by pi minus 2. And that equates out to out equals 0.5 times 1 times 1.25 minus 2. And further evaluation brings it to 0.5 times 1 times negative 0.75. And our final result is negative 0.375. Now we are in the negative part of our waveform. It made a sudden jump from positive 0.46875 to a negative 0.375. Let's see what happens when we continue. We increment the phase again. So phase equals 3.925 plus 0.98125, and the result is 4.90625. We've returned the sample value of negative 0.375 and head back to get another sample. We plug in our values again and we get out equals 0.5 times 1 times 4.90625 divided by pi minus 2, which results in 0.5 times 1 times 1.5625 minus 2, which equates to 0.5 times 1 times negative 0.4375, and our final result is negative 0.21875. So we increment the phase again. Phase equals 4.90625 plus 0.98125, and our result is phase equals 5.8875. We return the sample value of negative 0.21875 and head back to get another sample. Again, we plug in our values and we get out equals 0.5 times 1 times 5.8875 divided by pi minus 2, which equates to 0.5 times 1 times 1.875 minus 2, and that equates to 0.5 times 1 times negative 0.125, with our final result of out equals negative 0.0625. Now we are just about at 0 in our waveform. Can you guess what will happen next? It's likely the next increment will cause us to start over. So let's go ahead and increment again. Phase equals 5.8875 plus 0.98125. Now phase equals 6.86875. We return the sample value of negative 0.0625 and head back to get another sample. But now the value of phase is greater than 2 pi. So now we must take 6.86875 and subtract 6.28 from it. Now phase equals 0.58875. We are less than pi again, so we go back to using the if method. Now we plug in our new numbers, and out equals 0.5 times 1 times 0.58875 divided by 3.14, which evaluates to out equals 0.5 times 1 times 0.1875, with a final value of out equals 0.09375. We are now going back up in values in the positives of our waveform. To review, our output values in this exercise are as follows: 0, 0.15625, 0.3125, 0.46875, negative 0.375, negative 0.21875, negative 0.0625, and then 0.09375. We are cycling between samples very fast due to the 5000 Hz frequency, so these values change quickly. If I had chosen a much slower value, it would have taken hundreds or thousands of steps between samples before we completed a full cycle, so I chose to use a high frequency to cycle through them quickly. Having the oscillator explained, we now understand how we get one sample at a time. Now let's hear this basic saw project run on your BP Synth. It is very simple to upload. First we're going to open up the IDE, and then we're going to import the project. Existing projects, and from your BP Synth code folder you're going to find BP Basic Saw. Now the one I'm using is a copy on my desktop, so I can alter the code for demonstration purposes. Once it's imported, you can go ahead and open this up, go to Core, Source, Wavegen.c. And what we're looking for is right here, F0 200. This is our frequency, 200 Hz right now. So let's leave this open. Now we're going to open up our ST-Link utility. Now let's plug in our dongle, and up here where it says Program Verify, click on that. And you need to find your BP Basic Saw project folder. Now usually this will be inside of here in your BP Synth code, but I'm going to use a copy of it from my desktop so that I can alter it without having to alter the original one. So in the BP Basic Saw project folder, go to Debug, go to bpbasicsaw.hex, double click on that. You should see a dialog here. This is the programming dialog and should be ready to hit start. And as soon as this is done loading, we should hear a loud buzzing sound. Okay. I'm going to turn this down a little bit. So that is a 200 Hz sawtooth waveform that we're hearing right now. But let's say I want to double the frequency to 400 Hz. So right here I'm changing F0 to 400. Going to go up here to the build, which is this little hammer up here. Just click build. You'll see down here some dialogue going on here. 0 errors, 0 warnings. It looks like everything's good. Go back to the ST-Link utility. Click on Program Verify. Now you have to go back and browse for the folder that you have replaced. And by my date and time settings here, I can tell that this is a different file now. So now I'm going to double click on this, hit start, and the tone should change. Now it's twice the frequency. So let's double that frequency. Go back over here, change 400 to 800, hit build. Go back to Program Verify, browse for the file again, double click on it, click Start, and now we can hear that it's twice the frequency as it was before. Let's do it one more time. Now let's go to twice that frequency, 1600. Browse for the file again, double click, click Start, and we can hear that's pretty high pitched now. I'm going to go ahead and mute that. So now you can see it's fairly easy to go in and change something in the code, build it, then quickly go back here and find the file that you just built and reload it. And like I said, when you click on here, you have to go and browse for your file again and reload it. Otherwise, it's just going to reload the previous file, which is in the buffer of the ST-Link program. See, right here is the device memory. Here's the file. Now this file will stay in the buffer of this program, and if I hit Program Verify and hit Start, it's just going to reload this file. In order to change this file, I have to browse for the changed file, the one that's been updated. Then when I double click on it, it's going to update the file inside of here. And then I'll be able to click Start, and then it will upload the newest version. So practice this again a few more times to get a feel for how you can modify the code and upload it again to test the results. If you want a fully working synthesizer again, all you have to do is go back here to Program Verify, browse, find your BP Synth code folder, go to your BP Synth final folder, debug, and then select that folder and then load it, and you should be back in business. In the next lesson, we will conclude our study of Make Sound with conversions of our 32-bit float sample values into 16-bit values that the digital analog converter will use.